So today's notes put everything, all the formulas in one place for you to make studying a little easier. So it's got a bit of a review and then some new formulas as well for the quadrilaterals. So when we start with a circle that we've talked about before, your area equals pi times the radius squared. So if you need to draw a little picture of your circle, remember the radius is going from that center point to a point on the circle. If you were given the diameter, remember to cut that in half so you could find the radius that way too. In circles, we also talked about the area of a sector, like the area of a piece of pie. So you will take x and divide it by 360. Remember, x is your central angle measure, or sometimes they give it to you as an arc measure. Remember, they're the same. And then you're multiplying that by the area of a circle, by the pi r squared. So there's the picture. Remember that you're just finding the area of this slice of the circle. And then we've talked about a triangle that your area is 1/2 times the base times the height. So if I drew in this obtuse triangle here, my height has to be perpendicular. My height is really drawn on the outside of the triangle. A lot of times we use right triangles because we know that the legs are always perpendicular, but we don't always have to. Then we're talking about a square today. So since it's a quadrilateral, you could use the base times height, or since you know that these sides are congruent, your base would be the same as the other side length. It'd be the same as the height, so we could just say base times base or base squared. If it's a rectangle, you'll have your base times your height. This time, your base and height are different lengths, but they are still perpendicular since rectangles are made by right angles. Oops. Okay, we also have a parallelogram. Again, it's still base times height, but make sure that you're not using the side lengths for the height. Okay, that height has to be perpendicular to the base. Could be on the inside of the figure, could be on the outside of the figure, but it must be perpendicular. Same thing for the rhombus. You are not just taking your base times your base, like you would for a square, even though all the sides are congruent. You have to find the measure of the height, and that's got to be drawn perpendicular to the base. When we have a trapezoid, your bases, those parallel sides, are different lengths. So we're going to find the average of them. We're going to add the 2 up, and then divide by 2, and then multiply that by the height. Again, these sides here, the legs of your trapezoid, are not the height. It must be perpendicular to the bases. And for a kite, we're going to use those diagonals going from one vertex to the one that's not next to it. This whole length is diagonal 1. Diagonal 2, connecting these non-adjacent vertices, it's going the whole way across. We are going to multiply those together, diagonal 1 times diagonal 2, and then divide by 2. Then if we have an irregular figure made up of known shapes, we're going to add up all the areas of those different shapes. We've looked at this a little bit before. And we are looking at irregular figures on a grid, like in this picture below. Sometimes you might see this represented as like a lake on a map that we were trying to find the area of. So we have a new formula for that. When we talk about the letter I in the formula, this is included squares. They are completely on the inside of the figure. They are full squares. We have the letter B standing for boundary squares. Okay, those are squares that are on the edge of the figure. They're like half in and half out. They're not complete squares. They are just partly containing the area. And U is going to stand for the area of one square on our grid. So here's our formula. We're going to take all of the included squares. We're going to add those to half of the boundary squares because they're half in, half out. Whatever that total is, that tells us how many squares are part of the area, and we're going to multiply it by the area of each square. So we're going to look at this figure. I would maybe use two different colors when we're counting, or you could count one direction and flip your page upside down, and then your numbers would be going the opposite direction, or maybe you just put a square or a circled dot when you're counting these up. But as I'm going through, here's one whole square that's completely on the inside, 2, 3, 4, and we'll keep going. This is just an approximation, so if we're a little off, that's okay. Some people might think, some of these squares are completely in. Like I could see this one either going. Some people might argue that it's completely in. Some might say that it's a little out. So this is just a rough approximation. I'll be sure on your quizzes and tests to make it super obvious. But for now, this one's what we're working with. So I have 12 of those full squares. Here's where I would want to switch colors. I have to go through, and if the squares contain any part of our lake, any part of the area, I'm counting that up as well. Just kind of working around the edges to make sure I don't miss any. These are all of my boundary squares. Even if it's just a little tiny piece, you still count it as containing some of the area. Some might argue that that has part of a square. Some might say that it doesn't. Again, it's just an approximation. I'm going to say that this one is including this little piece there. So I ended up with 44 boundary squares. When I'm looking for the area of one of those squares, I would have to take this length here of 10 that they told us. Since it's a square, I'll just square it. Each square is really 100 units squared. So for my area formula, I'm going to substitute in what we know. That my included squares were 12. Those were my full squares. Then I had 44 squares that were half in, half out, so I multiply them by a half for my boundary squares. That gives me total squares on the inside, and I need to multiply that by 100 since each square had 100 square units. All right, when we add that up, we end up with 3,400 units squared on the inside of that crazy looking shape.